I'll just give a couple of minutes there for everyone to join in. My name is Sheena Fennell and I am hosting this webinar today. So we'll just give a couple of minutes there and we'll get going with Dr. Brian Ward's presentation. Okay, so welcome everyone to COREX's seminar series as we've just started for this year. And it's COREX, for those of you that haven't heard of us, is the Centre of Ocean Research and Exploration here in NUIG in Galway. And it's basically brings together all of the PIs that are involved with any marine research. So without further ado, we'll go on to our guest speaker, which is Dr. Brian Ward. He is a senior lecturer here in the New School of Natural Sciences, and he graduated with his PhD from the Department of Oceanography here in 1999. From there, he had a 2-year Marie Curie Fellowship in the Geophysical Institute of Bergen in Norway. And following on from that, he had a number of positions. The first position in NOAA in the Atlantic Oceanographic and Met Lab in Miami in the US. And from there, he spent 4 years in the Woods Hole Oceanographic Institute. Following on from there, 2 years in the old Dominion University, and he returned here to NUIG in 2008. So the webinar today is really about his broad overview of his research activities and a brief overview of his current research projects. And we would just like to thank him for coming today to agree to give us this webinar. We'd also like to thank Mohan as well, who has been fundamental in setting up this webinar. As we go through, if you'd have any questions, please just pop them in the Q&A and I'll give them to Brian then at the very end of the session. Okay, Brian, I'll hand over to you now.
That's great, Sheena. Thanks very much. You can hear me okay? I presume so.
All good.
Yeah. So today I'm going to talk about open ocean observations of the coupled ocean-atmosphere system. And to start off this presentation, I'm going to show this iconic graph of the CO2 concentration in the atmosphere. So these measurements were started by a scientist at Scripps Institute of Oceanography on Hawaii in the late 1950s. And this time series has been maintained up to today. And so what we're seeing here is that there is a clear rise in CO2 concentration since these measurements began. The pre-industrial concentration of CO2 is estimated to be 277 parts per million. So that's back in 1750. So since then, we have seen a strong increase in carbon dioxide. And today we have a concentration of 414 parts per million. And there doesn't seem to be any decrease in this concentration. And of course, this is what's driving climate change. So carbon dioxide in the atmosphere is what we're trying to reduce. There's a big meeting next month in Glasgow, COP26. And one of the main objectives of this will be to see if we can bring down this concentration in the next several decades so that we can avoid a 2-degree increase in global temperatures. So what's causing this increase? Well, fossil fuel emissions are largely the culprit for driving the increase in CO2 concentrations in the atmosphere. And these are estimates of the emissions in gigatons of carbon per year. So they're the flux of CO2 being emitted into the atmosphere, going back to the late 50s. And so you can see that there are decadal estimates within this time series. So for the 1960s, it was estimated that there was 3 gigatons of carbon per year. Up till the previous decade, 2010 to 2020, we're now looking at 9.6 gigatons of carbon per year. So these are annual numbers. So these numbers I'm giving of 9.6, it's 9.6 gigatons of carbon per year that are going into the atmosphere, largely driven by fossil fuel combustion. There's also a contribution from land use change, but the estimates are that the fossil fuel emissions contribute a little over 80%, and land use change contributes close to 20%. So what happens to the CO2 that goes into the atmosphere? Well, this graph here, taken from the Global Carbon Project, makes estimates of both the emissions, so the sources, and the sinks. And so the gray and orange areas of the graph are the emissions, and then we have the dark green, the light green, and the blue, which are the sinks of CO2. So CO2 gets emitted into the atmosphere, but it doesn't all remain there. Some of it goes into the land, so the terrestrial biosphere. And the third reservoir of CO2 is the ocean. And so this partitioning of the CO2 in the atmosphere gets distributed between, some of it remains in the atmosphere, some of it goes into the land, and some of it goes into the ocean. And as we can see that as the emissions increase over time, the sinks have also been increasing over time. And so we're mostly, this talk is concerned with the ocean sink of CO2. So here we have a graph of the sink of CO2 going back again to the late 50s, early 60s. And we can see that as the CO2 in the atmosphere increases, the CO2 into the ocean also is increasing in lockstep. So going back to the 1960s, we see that the ocean uptake was estimated to be 1 gigaton of carbon per year. And comparing that to the most recent decade, we see that the ocean's uptake is up to 2.5 gigatons of carbon per year. So there are many ways by which this ocean uptake is estimated. So there are several models here, which are in the green lines, the green time series, and the black time series is an average of all of these models. But we can also use an observation-based ocean sink, and that's shown in dark blue here. And what's interesting about this is that the observation-based estimate only commenced in the mid-1980s, and it's based on in situ measurements of ocean PCO2. But you can see that since the early 2000s, the models and the observations have diverged. So the observations indicate that the ocean is taking up more CO2 than the models, and this is still an open question. So one of the open questions is, which is the most accurate method for determining the ocean CO2 sink? And the second question is, will the ocean continue to take up CO2 at the same rate as CO2 is increasing in the atmosphere? So as I mentioned, there are discrepancies between the model and to focus on the observational based estimates. This requires direct measurements of the partial pressure of CO2, both in the ocean and the atmosphere. So in the atmosphere, the concentration is a little over 400 parts per million, or 0.04%. If we want to calculate the flux of CO2, which is the number of moles of CO2 per meter squared per second being transferred between the ocean and the atmosphere, we need to be able to calculate that based on this equation here. So this equation describes the flux of CO2 between the ocean and the atmosphere, and it requires measurements of the delta PCO2. So that's the partial pressure of CO2 in the atmosphere minus the partial pressure of CO2 in the ocean. So if the partial pressure in the ocean is greater than the atmosphere, we'll have the flux out of the ocean. And if the partial pressure is greater in the atmosphere than the ocean, then we'll have a flux into the oceans. This is basically driven by the second law of thermodynamics, where we see that the flux is driven by the direction of the higher partial pressure. But in order to calculate the fluxes, we also need to know the transfer velocity. So the transfer velocity here is denoted by the symbol K. And we don't have a direct measurement of this. So the only availability to us to calculate those fluxes is to use a parameterization. So the parameterization that's most widely used is one based on wind speed. So K is a function of wind speed, typically wind speed squared or wind speed cubed. But this assumes that wind speed is responsible for the generation of turbulence in the ocean, because the transfer velocity is really driven by how much turbulence is available in the ocean. And of course, wind is a big source of turbulence into the upper ocean, but there are other processes which also contribute to turbulence, which are not taken into account from this parameterization. So for example, breaking waves is a means by which we can inject turbulence into the ocean. And of course, breaking waves are intimately related to wind. So we're going to look at some of the processes governing breaking waves and some of our observations of breaking waves, but these are not directly included in many of the flux estimates. So what we're doing here at NUI Galway is carrying out research which are concerned with the processes which contribute to air-sea exchange so that we can improve the estimates of the global CO2 fluxes. So basically what we want to do is take this equation and look at the transfer velocity and see how better we can understand and parameterize the transfer velocity with the processes that govern it. So much of the research is driven by SOLAS, which is a program called the Surface Ocean Lower Atmosphere Study. This program has been around for about a little over 20 years. And the focus of this program is to view the ocean and the atmosphere as a coupled system. The most recent science plan was published in 2015 and was broken up into 5 themes. And one of those themes was concerned with the air-sea fluxes of mass and energy. And so this schematic here identifies some of the major processes which are responsible for these air-sea fluxes. And so we can look at wind is obviously a major driver of air-sea exchange. So the stronger the wind blows over the ocean, the more turbulence gets injected into the upper ocean. That erodes the molecular boundary layer at the ocean surface, and this causes an enhancement of gas exchange here. Gas, mass, heat, and energy gets exchanged in directly proportional to the wind speed, or as a function of the wind speed. Another process which I show here is the breaking of waves. So as the wind speed increases to a certain point, waves begin to break, and this causes highly localized additional fluxes. So localized additional fluxes of heat and gas and momentum are exchanged between the ocean and the atmosphere. Another process is rain. So rain falling on the ocean can have a stratifying effect. So you have fresh water sitting on top of salty water, and that can serve to diminish turbulence at the ocean surface. So it's like if rain falls on the ocean surface and is trapped there, there's a freshwater pool trapped at the surface, that can inhibit turbulence, and it will take some time for the turbulence to break down the stratification so that the exchange can recommence. So turbulence, again, is a central process for air-sea exchange. We represent it here by 3 different processes. Turbulence can be generated by wind, which is considered to be the most prevalent process, but there are also waves. So breaking waves will contribute to turbulence, as well as buoyancy. So buoyancy, you can think of a type of convection at the ocean surface. So we've observed the difference between day and night. So at during the day, you have the sun injecting heat into the upper ocean. When the sun goes down, the ocean starts to lose heat from the direction of heat is from the ocean to the atmosphere, and this leads to convective overturning in the surface ocean. So this is also a means by which turbulence gets generated and contributes to the air-sea fluxes. So in order to study this, we have developed tools to go to the ocean to make these measurements. So we've developed a direct method of measuring air-sea fluxes using the eddy covariance method. So this is a means by which, rather than parameterizing the fluxes, we can go to sea and directly measure the fluxes. We also quantify wave breaking using taking images of the ocean surface. And we've also developed an instrument which we call the air-sea interaction profiler. And this allows us to make direct observations of turbulence in the upper ocean. So I'm going to talk about these three different types of observations that we make when we go to sea. So the first one is the eddy covariance method. And so this equation here basically describes how fluxes are directly measured. And in order to measure them directly, we need the vertical wind, which is W prime, and we need at the same time the concentration of CO2. So if we can directly measure the vertical velocity of wind, and we can directly measure the concentration of CO2, we can directly estimate the fluxes by taking an average over typically 30 minutes or so. So we can resolve the fluxes of CO2, which are driven by these turbulent eddies, over time periods of approximately 30 minutes. So up until fairly recently, there's a publication here by Edson et al., which compares two methods of directly determining the air-sea fluxes of CO2. One is called the dual tracer method, which requires taking water samples of two different gases with two different diffusion rates over several days to weeks. So I think this experiment was carried over 3 weeks, and you can see from this study, there are 3 data points associated with the dual tracer method. The blue scattered data points are derived from the eddy covariance method. The main point here is that there's an enormous amount of scatter. So up until fairly recently, the last 10 years, making eddy covariance measurements in the open ocean were difficult to carry out because of the scatter that we can see here. So one method to get around this was proposed in 2010, and that method involved the removal of water vapor from the airstream. So we have a typical eddy covariance setup here. So there's a mast at the bow of a ship. It's got a sonic anemometer, which measures the 3 directions of the 3 components of the wind speed. So the U, V, and W. So the 2 horizontal and the vertical component. And then there's an air inlet near where the sonic is located. And this draws the air through a infrared gas analyzer, which measures the concentration of water vapor. Then that air stream is passed through a dryer, which removes all the water vapor. Then it's passed through a CO2 analyzer. And based on this, we can calculate the CO2 fluxes before it's dried and the CO2 fluxes after the airstream is dried. And so this plot here shows the wet airstream, the estimates of the fluxes, but in this case, we inverted the equation and we calculated the transfer velocity. So we have direct measurements of the fluxes, and we have direct measurements of the delta PCO2. So if you recall that the flux is proportional to the delta PCO2 times the transfer velocity. So if we can measure the fluxes directly, we can estimate or directly measure the transfer velocity and plot that as a function of wind speed. So we've done this over here on the left with the blue data points, and you can see that there's a significant amount of scatter associated with it. But when we look at the plot on the right, the water vapor has been removed, and we see that the scatter is much constrained. And from this, we can make better estimates of parameterizations of the transfer velocity. So what we're trying to do here with this method is to better understand the transfer velocity so that we can better calculate the global air-sea fluxes using the indirect method of the delta PCO2 measurements. So again, there are two methods by which we can measure the fluxes. There's the direct method using the eddy covariance. So for that, we need the vertical wind, and we need the concentration of CO2. And then there's the indirect method, which relies on measurements of the difference in partial pressure of CO2 in the ocean and the atmosphere in combination with a transfer velocity, which must be parameterized. So that is where the potential errors occur. So if we could go out and make eddy covariance measurements on an operational basis, then we would get around this limitation of having to parameterize the transfer velocity. But that's simply not possible because eddy covariance doesn't lend itself to an operational type of measurement. And so we have to rely on the delta PCO2, which is relatively straightforward in combination with the transfer velocity. Okay, so moving to some of the other processes that I mentioned in the opening slide, and one was wave breaking. So we've made observations of wave breaking at the ocean surface using taking images at the surface. So we mount a camera on the ship, we point it over the side, and we get a typical image that you see here on the right-hand side. And what you're looking at are two breaking waves. So the upper one is, it's called a stage A breaking wave, and that is because that is the active breaker that's currently occurring in this image. And the bottom breaking wave or white capping event is a stage B, and that's essentially the foam patch that remains at the ocean surface after the active stage A wave has broke. And so we found that stage B, the lifetime of the stage B type of white cap is a function of surfactant. But we wanted to see what the difference is between stage A and stage B, because the theory is that the stage A type of wave breaking is what causes this localized enhanced flux of CO2, because you're essentially rupturing the surface. You're causing a very highly localized exchange between the ocean and the atmosphere. And then stage B is really just a signature of what's left on the ocean surface after the stage A white cap has occurred. So we went through approximately 120,000 images. So here is a typical processing step. We take our initial image, then we run a thresholding algorithm on it until we get where the white capping occurs, and you can see that this image contains, by inspection, you can see that it contains a stage A here and a stage B here. And so then what we do is we identify these regions of interest. And once we've identified the regions of interest, which is essentially where the white capping occurs, we define whether they're stage A or stage B. So in blue here, you see that we've defined this as a stage A type white cap, and in green, we define it as a stage B type white cap. And so we wanted to see how these two type of white caps could be parameterized, and what essentially what their behavior was with respect to wind speed. So again, there's a series of images up here at the surface. You'll see that the first one is taken at 3.6 meters a second, moving on to 7.4, 12.7, all the way up to 22.1 meters a second. And you see that at the low wind speeds, we have very little white capping occurring. And at the higher wind speeds, we have significant white capping occurring. And so when I say significant, we're talking about, at 20 meters a second. If we look at this plot on the bottom right, you see that we have maybe 1 to 5% of the ocean covered in whitecaps. And so these are attempts to parameterize it. So this has been an ongoing area of research for the last 4 or 5 decades. In fact, much of this research was carried out in Galway in the 1980s by, he's currently he's based in the US, Ed Monaghan. So he carried out much of this, this research in Galway here in the 1980s. So this is really a legacy of Ed Monaghan's research that's still going on today. So here we see that the parameterization, the data points that we get from our averaged white capping in blue are the stage A type, and in green we see the stage B type. So there is somewhat of a difference occurring between these two types of white capping above 10 meters a second. And the challenge will be to try and include these processes in the gas transfer parameterizations so that we can better calculate what the fluxes of CO2 are. And then the final tool that I mentioned is to study upper ocean turbulence. So the upper few meters of the ocean is a critical layer for air-sea interaction. And many of the physical processes controlling momentum gas exchange are concentrated up here. And so we developed this device called the air-sea interaction profiler, which is an autonomous microstructure vehicle that can profile from a maximum depth of 100 meters to the ocean surface and allows measurements to be formed in essentially undisturbed environment. So what we would do is we would determine where the mixed layer depth is in the ocean using a CTD, and then we would program ASIP to go approximately 10 meters below the mixed layer depth. And it would, this is basically how it operates. So this is a movie that was taken in a tank in Brest. So this is in a 10-meter section of the tank. So basically, the instrument is fully autonomous. We put it over the side of a ship. We program it to profile at a rate of about 20 minutes to 30 minutes. So it will drive itself down every 30 minutes using 3 thrusters that are located down here at the bottom of the instrument. It'll go down to below the mixed layer. Once it reaches its target depth, those thrusters switch off and it rises up under its own buoyancy. And as it's rising up through the water column, the sensors are all located up here near the top, and that's how it makes small-scale measurements of turbulence, temperature, conductivity, and light in the upper ocean. So here are what the sensors look like. We've got 2 shear probes. The 2 shear probes allow us to make estimates of the dissipation rate of turbulent kinetic energy, which is how turbulence is quantified in the ocean. We've got 2 microstructure temperature sensors. We've got a pressure sensor. We have a microstructure conductivity. So with the combination of temperature and conductivity, we can calculate the salinity. And with the combination of temperature and salinity, we can calculate the density. And so we can look at how the water structure of the mixed layer of the ocean is using very fine resolution, very high detail resolution from below the mixed layer all the way up to the surface. So the movie on the bottom left is taken from the surface as ASIP descends to 15 meters. This was taken in the subtropical North Atlantic. It was extremely clear. There was no biology in the ocean, so we could almost see all the way down to 50 meters. And you can see here that the instrument is coming up rising up through the water column, taking the measurements from these sensors, which are located on the top, all the way up to the ocean surface. So it was important to us to resolve these measurements all the way to the surface, because as one approaches the surface, this is where the scales tend to overlap, and this is where it's more important to resolve what's going on in order to understand what these processes governing air-sea exchange. So on the right-hand side, you see a typical recovery of the instrument. So we would go out on a ship. This is taken from the research vessel Nor. We went out of Woods Hole in 2011, and we sailed up to Greenland. I'm going to show some data from this cruise. And we deployed the instrument 4 times, and this is typically how it's deployed. We put the instrument into the small boat. The small boat, we climb into the small boat. It's launched into the ocean. It drives, about 100 meters away from the ship, and then the ASIP is deployed over the side. The small boat comes back. ASIP is left out, and 24 to 36 hours later, we recover it. So that's when we get the data. The only information we receive from ASIP while it's been deployed is its position. So it provides us with some housekeeping data, like the state of the batteries, but the most important piece of information that it relays back is its position, so that once the mission is complete, we can drive over with the ship and pick it up and recover it. And it's then that we recover the instrument that we recover the data. So as I mentioned, this cruise was out of Woods Hole. This is where it's located. The left-hand image shows that we're in the North Atlantic. This is the cruise track, and these orange points indicate where ASIP was deployed. So the main focus of this research cruise was to study air-sea gas exchange. And so this is a time series of much of the many of the meteorological parameters. So the upper panel indicates the wind speed. So the blue line here is wind speed. We have atmospheric pressure down below, so there's rain. But what we're really interested in here, what I'm going to highlight, is this deployment. So these vertical shades are when ASIP was deployed. So we had 4 deployments of ASIP during this time period. So during this particular deployment, deployment 3, you can see the blue line here is the wind speed, and you can see that there's a dramatic drop-off in the wind speed from about 10 meters a second to about 3 or 4 meters a second, and then it remained low until it ramped back up again. And so during this period, we had ASIP in the water measuring upper ocean turbulence. And so just to zoom in on that, again, this is the wind speed from that period in blue. So we have the wind speed in blue here showing that we dropped from 10 meters a second to about 4 meters a second. The wind speed basically stayed off until this time where it ramped back up again from 4 meters a second up to about 16 meters a second. And so we looked at the meteorological conditions, the large-scale synoptic meteorological conditions, and we see here that we're basically in the eye of a low-pressure system. So we passed into the eye of a low-pressure system, the wind dropped off, and we came out of that, and it ramped up very rapidly from 4 to about 17 meters a second. And so this is an opportunity for us to look at how the ocean responds to this sudden decrease in wind and a sudden increase again. So this upper plot again is the wind speed and the waves. So we see very little difference between the significant wave height in green, but the wind speed again has this step change function. And the lower figure here indicates the turbulence that we measured with ASIP. So ASIP was programmed to descend to 50 meters. We cut off the bottom 10 meters. So you're seeing the upper 40 meters of the water column here. So while the wind was blowing up to this point, which is about 2100, you can see that the turbulence was distributed in the upper 20 meters of the ocean. But almost as soon as the wind switched off, so it went from about 10 meters a second to about 3 or 4 meters a second, we see a rapid decrease in the amount of turbulence in the upper ocean. And essentially, the turbulence in the upper ocean remained switched off until such time as the wind ramped up again and the turbulence turned on. So this was a surprising result because we didn't think that the ocean would respond as quickly to this atmospheric forcing as it did, but it's quite clear here that the time response of the ocean to the turbulence injection from the wind is quite instantaneous. And so the other thing that's interesting is that this black line here is a means by which we can estimate the mixed layer depth compared to these two red lines below. So the difference between these two methods is that the black line was based on dissipation, but the red line is based on density. So during this period, throughout this measurement period, we're seeing very little change in our density profiles, but we obviously see significant changes in the turbulence profiles. So that means that the mixed layer depth, the estimates of the mixed layer depth are quite different depending on which parameter you use to estimate them. And of course, density is the most widely used parameter to estimate the mixed layer depth, but you can see here that just because the density profiles indicate that the mixed layer depth is down to 25 meters, it doesn't mean that the mixed layer depth is well mixed, because you can see that the turbulence in the upper ocean has essentially died off here below 10 meters, and it's constrained to the upper, within the upper 10 meters, which is where the mixing occurs. Anyway, that was an interesting result from ASIP. So one other cruise that we went on in 2010 was a 4-week cruise on a Canadian Coast Guard ship. So here's the location. This is Newfoundland here sticking out. This is where we deployed ASIP. We deployed it on 5 occasions during this cruise. And this is a picture of the Hudson, the Canadian Coast Guard ship on which we did this research. You can just make out ASIP sitting in front of the Hudson there. So there isn't a lot of, there isn't a very large surface expression. So without our GPS location, which we can receive via the Iridium satellite network, it's unlikely that we'd ever be able to find ASIP. So we had ASIP deployed on the 23rd of May here. And so these 8 images show the synoptic view of, this is sea surface temperature from one of the NASA satellites from MODIS. And essentially all the white areas are covered with cloud. The green areas are indicative of pixels which there is some cloud contamination, and the blue areas are what the satellite algorithm recovers as an accurate sea surface temperature. So the scale down here shows that the sea surface temperatures were in and around 1.5 to 2 degrees. And there are very few pixels in this region which we can recover a sea surface temperature from space. But as it happens, during this overpass on the 23rd, ASIP had been deployed, and this was the location, this red asterisk. And you can see that there is some cloud contaminated pixels. So we didn't get an accurate return of sea surface temperature, but the conditions at the ocean surface are shown here during this time. So basically we had ASIP out for about 6 hours, and this is UTC, so you have a time shift of about 3 to 4 hours here. So you can see that there's quite a complex temperature structure. So there's a cold tongue here at about 30 meters, which is not unusual for the Arctic region. But if we focus on the upper 10 meters, which we see in the right hand, so this moving image is a profile. The profile times are shown here in UTC, and you can see that we're developing a significant warm layer as the time goes on. So this is the time series over 100 meters, and this is the warm layer that gets developed as the sun rises in the sky, and we probably are around local noon, a little bit before here, and so what's interesting from this is that you get this warming that's occurring at the ocean surface. And typically this type of diurnal warming only occurs under conditions of low wind, high solar insolation, and zero cloud. So if one were to look at the satellite image, one sees that the whole North Atlantic area is covered in cloud. But in fact, we have observed that conditions in the upper ocean, which are only conducive to periods when there's no clouds. So again, low wind, so the wind speed is probably less than 2 or 3 meters a second. High solar insolation, so it would have to be above 600 watts per meter squared, and essentially no cloud. So satellite observations at the ocean surface don't always reflect what's going on. And so this is one of the reasons why it's important to go out and make observations, because there are processes that simply can't be observed from space. And in order to fully understand how the ocean and the atmosphere act as a coupled system, we need to be able to understand these processes. And so what's interesting to us is, if satellites cannot tell us how prevalent these diurnal warming events are, how can we get a better understanding of how frequently these type of diurnal warming occurs? Okay, so basically moving on to a few current projects that we have going at the moment. We're building a new version of ASIP. This is an image of it here. And the main difference between the new version and the old version is that we have a buoyancy engine. So what we'll be able to do is change the buoyancy of ASIP by changing the density of the instrument. So we'll move oil from an interior reservoir to an exterior reservoir. So if we move oil out, that means we increase the volume, the mass remains the same, so it becomes more buoyant. And if we want the instrument to sink, we take the oil from this external reservoir and pump it to the internal reservoir, and that allows us to make it more dense, and therefore it will sink. So this allows us to modify the buoyancy of ASIP, and will allow it to go up and down in the water column in a similar fashion to the way we do it now. So the advantage to using the buoyancy engine over the thrusters is that we will use less energy when it gets to change the buoyancy, and we can conserve the battery for doing longer deployments. So that was the main objective here. We've also changed the data acquisition system, so we've added a state machine. We've added new sensors, so we're going to make velocity measurements directly, which we didn't do before. We're also going to design it. We designed it in such a way that we'll have faster turnaround. So we currently require about 12 to 15 hours to recharge the batteries on ASIP. With this new system, we've designed it in such a way that it can be easily accessed. The batteries can be moved. Freshly recharged batteries can be installed, and we can move on. So we also have the flexibility to add new sensors. I see my time is moving on. Sorry to keep you. I'll briefly mention 3 other projects I'm involved with. One is to do with the Southern Ocean, and I'll be heading down to Antarctica in December on this South African ship, the Agulhas, and we'll be making measurements of carbon heat from the ship and from several drifters. ASIP will also be involved, and this is a Horizon 2020 project. Another project that will happen next May is we're collaborating with the Ocean Frontier Institute in Canada to study the biological carbon pump, again going back to the Labrador Sea. And so we'll be leaving from Galway on the Celtic Explorer, spending 36 days at sea. So we'll have about 22 days of sampling in the Labrador Sea to try and better understand the biological carbon pump. And then one final project I'll mention here is that we're developing some technology using SFI grants to measure carbon in the ocean with only 1 milliliter of seawater. So typically, to measure dissolved inorganic carbon in the ocean requires of the order of 1 liter of seawater, but we want to be able to do this with 1 milliliter so that there are potential for deployments on Argo. So my conclusions: the ocean and atmosphere are a coupled system, and therefore they should be studied in tandem. The upper few meters of the ocean are critical for processes controlling air-sea exchange, and a complete description of this coupled system requires observations of fluxes, upper ocean turbulence, and waves. And I leave it at that, and thank you for your attention.
Thanks very much, Brian. That was a great presentation. I'm going to jump straight into some questions. Just from Roger, with COP26 later this year, do you agree that it is important that everyone who cares about climate change and loss of biodiversity should write personally to their political representatives and make sure they know their views? Politicians.
I think it is critical to write to the representatives. I mean, my understanding is there's going to be 30,000 people attending COP, and obviously Ireland will have a delegation there. And I think that, considering that our ocean territory represents 10 times that of our land territory, then the ocean should play a role in Irish climate policy. And so understanding the role of the ocean in the CO2 uptake, I think is critical for this. And I suspect that the ocean is going to play a big role in this COP. For the Paris Agreement, the ocean wasn't really given a lot of emphasis. The biggest concern was to try and keep the remove CO2 from the atmosphere and keep the world from heating above 2 degrees Celsius. But the indications are that there will be more emphasis on the ocean and blue carbon, which is where the world's ocean takes up carbon. And this is not really taken into account in many of the national estimates. And so I think that by letting our representatives know that Ireland is an ocean nation and that the oceans should play a role, then I would most definitely encourage people to write them. So yes.
Great, thanks, Brian. I just want to ask if anyone else would like to pop in. If you have any questions, just pop them in the chat there. And Brian, I might, just apologies that I'm on the phone. Can you just check that the chat hasn't gone to you, that there's any questions in your chat function, Brian, please?
There's no questions here, no.
Yeah, perfect. Yeah, that's great. Okay, I suppose, can I just ask you one question, Brian, with regards to, I suppose, it was the Labrador sea warming and the diurnal heating that is really interesting. And I am assuming that at this stage that isn't captured in any modelling that happens, and that I would perceive it would be very, very important for that to be captured when we start looking at that. I suppose what the upper ocean is doing. Like, is there in any of the upper ocean modelling work that you've seen, is that captured at the minute or not?
Not in terms of global modelling. So this isn't a process that gets captured by any of the parameterizations for CO2 exchange or heat exchange, but there is an awareness that this should be taken into account. For example, when we're calculating the air-sea heat exchange. But it's not done on an operational basis. And it's certainly much of the effort to observe the diurnal warming has been done from satellites, but our observations show that satellites are just not capable of observing all of the diurnal warming events that occurs. And so we don't really know how prevalent this process is. So anywhere you typically see, high solar insolation and low winds, which is around the subtropics, you can see this type of warming occurring in the upper few meters. But it can't be observed with a CTD, and it can't be observed with an underway thermosalinograph. So it's a difficult process to observe, and I think we don't really know what the overall effect is on it globally. So yeah, I mean, it should be taken into account for sure.
Okay. Yeah, Roger, just another question there for Roger. People don't seem to worry about 1.5 Celsius. They would worry if it was body temperature. And that's true. Yeah, it is true.
Yeah.
It is true. Okay, so I think that's it on the questions. I'd like to thank everyone who joined the webinar today, and also our thanks to Dr. Brian Ward for taking the time out to give us this presentation. As our Mohan said through the Ryan Institute, that it will be available on YouTube, and it is available on our Ryan Institute YouTube channel. So if you do want to go back and listen to it again, you're more than welcome. And yeah, we would just like to say thanks very much, and do keep an eye on our Twitter, because we will be doing a few more webinars over the coming months.
Okay, thank you.